to talk about index theory. And I want to start off by defining what an elliptic differential operator is. So that's sort of the first part of the talk. Elliptic differential operators. Operators and the index. I should maybe give a general reference here. So a book that I learned a lot from, that's not particularly easy to digest, is the book by Spin Geometry by Lawson and Michelson. So it's slightly intimidating since it's a thick book, but if you pick and choose parts out of it, you can gain a lot from it. All right, so what are elliptic differential operators? So let's start with sort of the basic case. So the basic case, we just talking about functions on Rn. So I look at smooth functions on Rn, and for my purpose, I want to think of complex valued functions on Rn. So these are maps from Rn into C, which are smooth. And a differential operator here is a linear map from functions to itself. Linear map. Such a linear map is called a differential operator, is a differential operator. And since I'll say the words a lot, I'll just write DO from now on. Differential operator of order K. Well, if it has the following form. So suppose that you have a function f, and you want to apply this map to it. Then this is a new function. This new function should have the following form. You take the old function, you differentiate it a bunch of times in a bunch of directions. So you say differentiated alpha 1 times in the first coordinate direction, alpha 2 times in the second coordinate direction, up to alpha n times into the nth coordinate direction. And then you get a new function here. And then you multiply this by some other function, which will depend on alpha. That's just another smooth function on R. And you sum up for all alpha smaller or equal to k. So here the alpha is a multi-index, alpha 1 up through alpha n, where these things are natural numbers. The sort of value of that is sort of the sum of these things. Okay. So that's sort of the form that the differential operator takes. And to say it's a differential operator of order k, I also want to say, oh, the kth order terms are not all 0. Sort of, and the coefficient here is not identically 0 for some alpha of degree k. Okay. So that's the most basic situation of a differential operator on Rn. Now you can make it more general. By saying, oh, instead of just having complex value functions, we have functions on Rn with values in some complex vector spaces. So let's say E and F are complex vector spaces. Then you look at an operator D from the smooth functions of Rn with values in, say, the complex vector space E into functions on Rn with values in this other complex vector space F. And you want that to be a linear map. And then is a differential operator of degree of order k if, well, if it has this form, but now the understanding, of course, needs to be a little bit different, right? Since if you differentiate this e-valued function a bunch of times, you still get an e-valued function. So that means this thing here needs to turn this e-valued function into a v-valued, into an f-valued function. So in other words, it should be a map from Rn into the homomorphisms from E into F. So if D, if the differential operator, if this operator has form, the form star, with the understanding that now the A alpha, which before was a function with values in C, is now a function with values in the linear maps from E to F. So that if you apply this to an E-valued function, you get an F-valued function. Okay? So that's the differential operator acting on vector-valued functions. Now we're going to globalize it and talk about differential operators on a manifold. So this is the first step in the generalization. And the second step of the generalization, the E and S will be vector bundles, smooth vector bundles over the manifold X.
Mm-hmm. So do I just naively think about it? You have to say what you mean by differentiating a vector value function to begin with. So you have to have some kind of structure on the vector. But you just identify the vector space.
Oh, my vector spaces here, I'm thinking of a finite dimensional.
So you just identify Rn and just differentiate.
Yeah, exactly, exactly. So if you have infinite dimensional vector spaces, then the topology matters, but here, nah. So this is of finite dimensions. Okay, so if you have E and F vector bundles, then you can look at sections of X with values in E. And you have a vector space here, which sort of generalizes the space of vector-valued functions on a manifold. And if you have a linear map D from sections of E into sections of F, that is a differential operator of order K. If, well, if it is locally of this form, if D is locally of the form star. Okay, so that means, yeah, you trivialize the your vector bundle. You look at your charts, and then in a little neighborhood at every point, well, a section of a vector bundle is just an e-valued function on a piece of Rn, and similar over here. And then with respect to those local trivializations of your vector bundles and your charts for your manifold, that should have this form here. You could write it a little bit sort of more general. In particular, you could ask, well, what kind of thing is then this A alpha? So now, in this context, the A alpha is just a section of the homomorphism bundle of E into F. Right? So if these happen to be the trivia vector bundle, oh, that's really just a map, smooth map from X into the linear space of linear maps from E into F. Okay, so that's what differential operators are. So let me give you quick examples here. Examples of differential operators. Well, suppose you have a vector field. On a manifold X. What's a vector field? Well, there's the algebraic definition which says, oh, a vector field is just a derivation of the algebra of functions on this manifold. So also known as a map D from the smooth functions of X to itself, which is a derivation. Oh, if you look at it, what it is locally, well, you differentiate in one direction, right? So this is a first order differential operator. So this is a differential operator of order 1. Slightly elaborating on that, you will all know the de Rham operator, right? The de Rham differential. So that is a linear map from the k forms of X into the k+1 forms on X. And to recall, k forms on X are sections of a certain vector bundle over X. Namely, you take the cotangent bundle of X, and you take its kth exterior power. And then, of course, this one here is also a space of sections, namely of the k plus first exterior power of the cotangent bundle of X. And yeah, this is also a differential operator of order 1.
In both of these examples, they're not complex unless we complexify, right?
Yeah, I'm wavering a little bit on that. So yeah, that works in the complex world. Okay, I'm sorry. Yeah, thanks for reminding me. I should repeat the question. So Mark was asking, oh, but here we're talking about complex vector bundles. So yeah, I need to complexify to make it correct. Or I need to say, oh, everything here works as well with real vector bundles. And it's also only for later purposes. That's word complex. No, absolutely. Okay, now I want to define what it means for an operator to be elliptic. And that is defined in terms of its so-called principal symbol. So definition. So let's say D is a differential operator. Well, let's do it explicitly. So let's say it goes from sections of a vector bundle E to sections of a vector bundle F on a manifold X. There, suppose this is a differential operator of order K. The principal symbol of D is a vector bundle map from the pullback of E into the pullback of F. And I call this sigma of D for principal symbol of D, where the pi is just a projection map from the cotangent bundle of X into X. So what does this do? So I need to describe what's the linear map on each fiber, right? So on each fiber. So this is a vector bundle over the cotangent space. So let's take a point in here. So if I have a point in the cotangent space, total space of the cotangent space, it sits over some point x, right? So let's say xi is a point in the cotangent space over a point x in our manifold x. Then I want a linear map from the fiber of the pullback bundle over xi into the fiber of the pullback bundle over the same point, right? I want a linear map. So this linear map will be, I'll denote that sort of the vector bundle map at the point xi. So what is the fiber of this pullback bundle? Well, that's the fiber over the image of xi under the projection map. So that's x. So this one here is just the fiber over x of the vector bundle E. And similar, this is the fiber of f over the point x. So now I need to write down this map here. So, okay, what should that be? Well, I already have maps, namely A alpha at the point x, right? That A alpha was a vector bundle map from E into F. So in particular, if I evaluate this vector bundle map at a point x, I get a linear map from the vector space Ex to the vector space Fx, right? So this map will be made from those linear maps. And so I want to write it more precisely. So this will be a big sum of those things. But what's weighted in there is the psi. So I need to explain what do I mean by psi to the alpha, right? What this means is I work locally here. So I'm thinking I'm sitting inside a coordinate chart. If I'm sitting inside a coordinate chart, then this cotangent vector at the point x can be written in terms of the basis, right? The basis of the cotangent space is given by dx, 1 up through dx k, up to dxn, sorry. So it will be some linear combination of this thing here. Sum from 1 up to n. Okay? And then this psi to the alpha is defined by saying, oh, this means take psi1 to the power alpha 1 times psi2 to the power alpha 2, blah, 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 times psi n to the power alpha n. So in other words, this is sort of a homogeneous polynomial of degree k sort of on the cotangent space. And so then this one here is a function on the cotangent space with values in the linear maps from Ex into Fx, which is homogeneous of degree k in the cotangent space. Any questions on that? Okay, that's the so-called principal symbol. All right?
So this is, why the cotangent space? I mean, I don't see the role it plays here because you're just taking a local chart. You could have done a tangent space.
That's true. So the question is, why are we working with the cotangent spaces when we do it if we work locally anyway, where you don't see the difference much between cotangent and tangent? So the reason is, say, think about a vector field as a first-order differential operator. What would be the symbol? Well, the symbol should be a function on the total space of the cotangent bundle or the tangent bundle. So I'm claiming, hey, if I have a vector field, I see a very natural way, a function on the cotangent space Namely, at every point in the cotangent space, I have a cotangent vector. Oh, I can evaluate that on the tangent vector that gives me gives the vector field to get a function. So no. So exactly. So this is a natural thing to do. So these things fit together. This local description fits together under transition functions, unlike if you try to do it on the tangent bundle. But later on, we will, in fact, sort of identify these things when we sort of do topological considerations. So.
I guess like the very pedestrian answer would be that differential operators are made out of partial derivatives. So how do they transform?
Yeah.
Yeah.
Right, yeah, that's,
Yeah. Okay, great. So that's the definition of a principal symbol. And that's sort of crucial now for defining what we mean by elliptic operators. Definition. So the differential operator of order k is elliptic if, well, now I say it in terms of this vector bundle map. So I have the principal symbol, which is the vector bundle map of the pullback of the domain vector bundle and into the pullback of the range vector bundle. If this one here, and let me say it at the point psi, if this map here is in fact invertible, well, it has a chance of being invertible, since it's a polynomial, homogeneous polynomial of degree k. Of course, it needs to be 0 at psi equal to 0, but we want it to be invertible for any non-zero psi. Is invertible for any non-zero psi. Okay. So notice, in particular, that means, that implies that the dimension of E better be isomorphic to the same as the dimension of F, right? Since this gives us an isomorphism then between the fiber over of E over X and the fiber of F over X. All right. So now an interesting question is, well, what are good examples of elliptic differential operators? So maybe I shouldn't have erased these things here, since we could ask in any of these examples, are these things elliptic? So for example, the de Rham operator, is that elliptic? Well, no, it doesn't have a chance of being elliptic, right? Since it goes from k forms to k+1 forms. Well, the bundles involved there don't have the same dimension generically, so no chance, right? According to that remark. So you might say, oh, but what about just a vector field? Is the differential operator given by a vector field, is that elliptic? And the answer is no. I mean, since it differentiates only in one direction, so if you test it on a cotangent vector on which this vector field evaluates to 0, then no, the principal symbol is 0 in that direction. So no, these previous examples are not elliptic. So note previous examples are not elliptic. But you can build an elliptic operator out of the de Rham operator as follows. So you need to do this move here. So you look at, say, k forms and k+1 forms. And there's a de Rham operator going this way. Now, if you have a Riemannian metric on X, there's also an operator going the other way, namely the adjoint of it. So now suppose X is a Riemannian manifold. So then you have an adjoint here. This is the adjoint. of d, which is again a first order differential operator. And let me just say what it's characterized by. It's characterized by this adjoint property, so meaning the following. So take d star, you can apply that to a k plus 1 form. Let's say phi is a k plus 1 form. Then the resulting thing is supposed to be a k form. So suppose you give yourself a k form, say psi. Then you can take the inner product of those two elements, of those two k forms. Where this is an inner product that I'm going to describe in a minute on the space of k forms. Sorry, on, yes, k forms of x. And the requirement is that, yeah, you can sort of slide it over in the other slot and make it a d. So that should be equal to the inner product of this k plus 1 form phi with the k plus 1 form that you produce out of psi by applying the de Rham operator. So this is the inner product on k plus 1 forms on x. So how does this inner product work? Maybe do this on the side here. So suppose that you have two k forms, say psi 1, psi 2, or k forms. And k forms are sections of the kth exterior power of the cotangent bundle of x, right? So in particular, if I take a point in x and I evaluate this thing here, this is going to be an element in the kth exterior power of the cotangent space at the point x, right? And similarly, psi 2 will also be an element of that same vector space. Now, you have an inner product on the tangent space. That's going to give you an inner product on the cotangent space, and that gets you an inner product. So it has inner product that I denote maybe by this sort of round brackets induced by the Riemannian metric, which gives me an inner product on all tangent spaces. So then I can take these two vectors, take the inner product, so that gives me a number. So in other words, I have a function on the manifold x. And then I can integrate that over x using the volume form. So dvol is a volume form. So then that gives me a number, which is this inner product of psi 1 and psi 2. So in that way, you can define an inner product on all the differential forms, and then you can start talking about the d star. As a side remark, you can also express the adjoint d star in terms of the Hot star, but that doesn't matter for the context we are interested in here. Okay, so turns out neither of the operators d plus d or d star are elliptic.
So do I need my manifold to be orientable?
No, to talk about the adjoint, you don't need the orientability.
Oh, we're integrating a positive.
Yeah, yeah. I mean, you need to then talk a little bit about, like, what do you mean by volume form? So that would be a form, there would be a density, but
okay.
that all works out. Okay. So how do we get an elliptic operator? Here's what you do, is you define the so-called Laplace de Rham operator. And let me denote this symbol for it. That's obtained in the following way. You take the operator d plus d star. So you think of that as an operator which goes from all differential forms to all differential forms. Right? Since D produces a k plus 1 form out of a k form, this produces a k minus 1 form out of a k form. But if you add them, you can still view them as an endomorphism of all differential forms. And then you can square this operator. That's the Laplace de Rham operator. And of course, you can sort of multiply it out, right? So you could write it in this form. But then noticing that, hey, this is 0, and hence also the square of the adjoint must be 0, you can also think of it in that way. And if you think of it this way, then you see that, oh, you can really think of that as a map from k forms to k forms. Since the D star makes out of a k form, a k minus 1 form, but then you apply the D again, that produces a k form again, and similar over here. So the Laplace de Rham operator is really an endomorphism of omega k for every k. And so this is an elliptic operator. Okay. Now, what's cool about elliptic operators? Why do we even talk about that? So,
how are you doing sigma d psi as map from fiber from EX to FX? And obviously, just talk about the board that you're about to raise.
so the Laplace. So the question is, why is the Laplace de Rham
while you're talking about all this, I'll just direct this part of the board. I'm a bit confused about how this is a map from fiber from EX to FX.
So you're asking about this map here and the definition of this map?
Yeah, so it's like I think it's supposed to be like if you've got like a differential operator on Rn, then like the symbol of it is just supposed to be like a smooth symbol of the Fourier transform.
There's one way of defining it. You can do the pedestrian way. This is a pedestrian way of defining it. And the hard part here is, if you do it the pedestrian way, you need to show that it has the right transformation properties under transition function. But you're happy with the local formula, right?
So what Stefan's saying here is, a pullback bundle, a property of the pullback bundle is that the fiber is the fiber.
Yeah.
So C is an element of the fiber over X. So therefore, the fiber of the pullback bundle is the fiber of the original bundle over X.
So why is this a map from EX to FX then?
Well, because the top and the sorry.
These things are, right? These are linear maps from the fiber to the fiber. Sort of by definition of what we write down.
So why sigma d then? So sigma d is psi.
So now we add a bunch of these multiplied by these numbers here. So then each term here is still a linear map from EX to FX.
Can I say very pedestrian way of looking at it? So you're writing your differential operator in local coordinates. So you're looking only at the top degree, where the parts can contain the top, the highest derivations of highest degree, and then you replace all partial derivatives with just new variable. D over dxi becomes psi I. So that becomes a polynomial from space.
Yeah.
Instead of a differential operator. And
It's not supposed to be a linear map.
it's a linear. It's linear map in a different variable. It's a polynomial mapping size, but it's linear in. So all the coefficients are homomorphisms from E to F. They're just matrices.
Maybe if you wrote the symbol of the Hodge Laplacian,
So you get a
then
polynomial.
make it more.
Yeah.
C is fixed,
So
so it's not linear in C.
No.
But the alphas are linear maps.
Yeah, A alphas for each. So they are matrices, if you will, like.
So let's do
X to Fx.
example. So you could ask, well, what is the principal symbol of this Laplace operator? So the principal symbol of the Laplace operator at a point psi. So what kind of thing is that supposed to be? Well, it's supposed to be an endomorphism of the fiber of the vector bundle that the Laplace operator acts on, right? which is the kth exterior power of the cotangent bundle of X. So which endomorphism is that? It's a pretty boring one. It's the identity on this map, on this thing. But then, yeah, that can't be it, since it needs to be a quadratic polynomial of xi. So what's a quadratic polynomial in xi? Well, you take the norm squared of your cotangent vector xi. That's sort of the quadratic polynomial, right? And with values in the endomorphism of this particular vector bundle. So it does depend on xi, but it's also a linear map. For every fixed xi, it's a linear map of this vector space to itself. Mm-hmm. All right. So let's see. So I was talking about the Laplace-de Rham operator. That's an example of an elliptic operator. So, but I now wanted to talk about why do we care about this funny ellipticity condition? How is what?
How do we show that the signal is just this?
Well, one way to show that this is a true equation would be to write it out in local coordinates, and then you see that this is true. I won't do that. As I said, I mean, this is a survey talk, so I skip totally all details and all proofs, but I just claim a lot of facts that maybe I don't know the proof of myself, but that I read in books. Okay. So here's sort of the main theorem in the subject. It says if D is an elliptic operator on a compact manifold, and I'm always thinking of manifolds without boundary here, then you can look at the kernel of this elliptic operator, and it turns out the dimension of that space is finite. In similar vein, you could look at the co-kernel of this elliptic operator. Turns out that's also a finite dimensional vector space. So that's the major result, and that's why you care about this condition of being elliptic, since that guarantees that you have finite dimensional kernels or co-kernels. So you have numerical invariance that now you can work with. As I said, I won't go into the proof of that. Roughly speaking, suppose that you knew that your operator D is invertible, then obviously kernel and co-kernel will be trivial. Now you don't want to show it's invertible, since you just want to show that these numbers are finite, but you want to show that they're invertible modulo something called modulo compact operators. So that guarantees that kernel and co-kernel are finite dimensional. So you want to show invertibility modulo compact operators. So this is sort of like, you don't want to show that a map has an inverse, but maybe it has an inverse up to homotopy. This is sort of the analyst version of that, right? So now if you compose a differential operator of order k with a differential operator of order L, you get something that differentiates k plus L times, right? So that's a differential operator of order k plus L. Oh, but the identity is sort of a degree, an order 0 operator. So that sort of shows you're out of luck if you're trying to find sort of a pseudo-inverse in the world of differential operators. But there's a larger world of so-called pseudo-differential operators. And the ellipticity condition guarantees that, yeah, you construct inductively sort of something, a pseudo-differential operator, which is a sort of a pseudo-inverse to that original operator, in the sense that the two compositions that you can form are compact operators. So that guarantees the finite dimensionality of kernel and co-kernel.
Is that thing called the parametrics?
That's called a parametrics, is my understanding, yeah. Okay, it's just very, very roughly. Okay, but let me show you that this thing here lines up well with things that we know as topologists. So all of this talk about index theory has sort of a topologist slant to it, since most of the Audi members are sort of more topologically affiliated. So let me look at the case of the Laplace de Rham operator. So the kernel of the Laplace de Rham operator, that's known as the harmonic K-forms. K-forms. So this is by definition the kernel of the Hodge of the Laplace de Rham operator from K-forms on X to itself. Now, there's another way of writing the same thing. Maybe you can convince yourself easily that this is the same thing as taking the kernel of the de Rham operator from K forms to K plus 1 forms and intersecting it with the kernel with the adjoint, D star, going from K forms to K minus 1 forms. And then you have an obvious map from here into the set of closed K-forms. That's the kernel of this map, divided by the exact n-forms, exact K-forms. Sort of, which just takes a differential form, which is closed, since it lives in here, ignore this condition, and just look at its equivalence class in this quotient. Now, this one here is, by definition, the de Rham cohomology. Okay, de Rham cohomology of X. And by Hodge theory, this map here is actually an isomorphism. So there's Hodge theorem. So you can think of de Rham cohomology as being isomorphic to harmonic forms. Now we also know that you can have the de Rham theorem here, which provides us with an isomorphism of the de Rham cohomology and the singular cohomology. There's coefficients in now again, need to say R or C or so. I won't be careful about that. So this is a singular cohomology. And we know from topology that if we assume that X is compact, the singular cohomology will be finite dimensional vector spaces. These are finite dimensional for X compact. And now you see, there's sort of a very different analytic proof of that. Namely, using this theorem, we see that, the harmonic forms are finite dimensional as a kernel of this elliptic differential operator. So it's sort of neat that these things sort of really go hand in hand. The kind of things that we might know as topologists really line up with things that analysts know. Okay. Now, let me note that the vector space of harmonic K-forms, that's a subspace of all K-forms. So note the K-forms of X. It's a subspace of all differential K-forms. The note is that this space here actually depends on your Riemannian metric. On the Riemannian metric. Since the operator, the Laplacian, depended on that, and so, and you can see in examples that, no, as you change your metric, the space of harmonic forms really changes. However, its dimension is independent of, but dimension of that thing is independent of the Riemannian metric. So that might lead you to believe that, oh, that is maybe a general story. So whenever you have an elliptic differential operator, that the dimension of the kernel and co-kernel, those are finite by this main theorem, they should not depend on sort of the details. So in particular, as you deform your elliptic differential operator, you might think that, oh, the dimension of these things is independent of that. So this is not true. So note, or maybe a fact, important fact. So if you deform an elliptic differential operator on a compact manifold, then let me call that D. Then the dimension of the kernel of D and the dimension of the co-kernel of D might jump. So no, they can change. Even if you continuously deform it, the dimension does not stay the same. But if you look at the dimension difference, so if you look at the dimension of the kernel minus the dimension of the co-kernel, that quantity, that integer, is actually does not change in your deformation. Does not change. So that's why this is a quantity that has a much more topological feel to it, right? It's independent of these sort of quantitative data, like things like Riemannian metrics. So it's more a qualitative thing, right? So, and if you think of geometry as being sort of quantitative, in the sense that they care about volume of their shapes and the curvature of their shape. But you think of topology as qualitative, like as you deform your balloon, its geometry changes, but its topology doesn't, right? So that makes you think, oh, there should be something topological about this index. So this is called the index, this quantity, and this is called the index of this operator D. Now, the obvious question is then, well, it has this topological feel to it, so is there a topological way to calculate this index? So is there a topological way? To calculate the index of an elliptic differential operator. Okay. So that is the question that the index theorem addresses. It says, yes, there is a purely topological way to calculate this thing, and it has to do with Thom isomorphisms in cohomology in K-theory. And so that's the next thing that I want to explain. So the next part of my talk will be sort of a first step in this direction. Namely, we'll be looking at the principal symbol, but we want to think of it as a K-theory element. Sort of any questions on this part?
I have one potentially naive question.
Mm-hmm.
If you have an elliptic operator on Rn, can it have an infinite dimensional kernel?
Yes. Yes. So the compactness is essential, sort of the same way as sort of the compactness is sort of interesting to control the topology.
Right.
Yeah, harmonic functions.
Ah, okay, good, okay.
Okay. Second part of my talk will be about the principal symbol as a K-theory element. Okay. All right, so let me recall a little bit about K-theory first. So we'll suppose X is a compact space. And let me denote by vect of X the category of vector bundles. Over X. And again, I'm mostly thinking of complex vector bundles, but the whole story would go through with real vector bundles as well. So let me not worry about it at this point. Now, you probably all know how to make K-theory out of vector bundles by saying, oh, you look at isomorphism classes, and that's a monoid with respect to addition, and then you take the group completion of that. Now, I want to write it down in more down-to-earth terms, since at the end, I want to define sort of what is K-theory of X relative A. And for that, it's better to just do it a more sort of down-to-earth-ish. Okay? So K-theory of X, a more down-to-earth description, is defined as follows. You take pairs of vector bundle, say E plus, comma, E minus, where plus and E minus are just vector bundles over X. But you put an interesting equivalence relation on that. This is generated by sort of two moves. I mean, there's an obvious notion of isomorphism between two-such pairs, right? So if you have another pair and these are pairwise isomorphic, then yeah, then you want to declare them to be equivalent. So by isomorphisms of such pairs. Well, but you need to do something else in order to get inverses. And this something else is in the following way. So secretly, when we write these pairs of vector bundles, we really think of it as a difference of E plus minus E minus, right? So in particular, if you think that way, that means if you take a vector bundle and you add it to E plus and you add the same vector bundle to E minus, well, the difference doesn't change, right? And you express that by this equivalence relation. So you say, hey, if you add the same vector bundle F to both things, then you want to declare it to be equivalent to the original thing. So again, this is sort of the part of the equivalence relation that enforces you to say, oh, you really should think of these as differences of vector bundles, right? So the point of doing this one here is that this one here becomes an abelian group. And the addition is given by the direct sum of such pairs. So you add to such pairs by adding each of these components. And the point of this one here is that you want an inverse. And you can show that the inverse to E plus, comma, E minus is E minus, comma, E plus. So you might say, oh, why? I mean, if you add this to that, then you're getting E plus plus E minus, comma, E plus plus E minus, right? But why should that be trivial? Well, by this relation, right? Since that is isomorphic to the bundle. This relation in particular means that any bundle where those two terms are equal is equivalent to 0, right? And that's why E plus E minus, comma, E plus E minus represents 0 in this group. So this one here makes sure that you get an abelian group. Okay, let me do one more thing. Now I want to define relative K-theory. So if I have an open subspace of X, I want to define K of X comma A. And that has a similar description here, but it's a little bit more. I have not just two vector bundles, E plus and E minus. I also want to somehow say, I mean, what's the idea of relative cohomology? You want to say, oh, but it's sort of, its restriction to A should be trivial. Well, how do I recognize if such a pair is trivial? Well, if I find an isomorphism between them, right, then that pair is trivial. So somehow I want to have some data that tells me, oh, if you restrict these bundles, E plus and E minus, to A, then they become isomorphic. But in fact, I want to remember the reason they become isomorphic, right? Oh, okay, so I build in the reason in the definition. I'm saying, oh, I want a vector bundle map between there. So this is a vector bundle map. So notice that I didn't say it's a vector bundle isomorphism, just a vector bundle map. But the condition is that if I restrict alpha to A, then it becomes an isomorphism. Is an isomorphism. Right? So that guarantees that if I restrict this thing to the subspace A, oh, then the bundles become isomorphic, so this represents 0 in the K-theory of A. And again, I need to take suitable equivalence classes on these things to guarantee that I'm getting an abelian group in this way. So this equivalence relation is generated by, there's an obvious notion of isomorphism between those things, right? Of these triples, meaning it have an isomorphism between the plus parts and the minus parts, but they need to play with the vector bundle maps in between. Then I also want to allow it to stabilize. So I'm saying if I have one such thing with alpha, and that's equivalent to the thing that I get by just adding a vector bundle F on both sides, and adding to alpha the identity on F. Right? And one final thing, I want to say, oh, you can homotop the vector bundle map alpha, but keeping the condition that its restriction to A is an isomorphism. So homotopies of alpha, but still restrictions to A during this homotopy need to remain isomorphisms. Okay.
Why does this agree with the original definition when A is an null set?
I don't worry about it. I won't comment on it. I'm sorry. That's a homework problem, let's say.
The third condition is confusing me a bit because, like, it feels to me like 1 and 2, like, it feels to me like 1 and 2 should be equivalent to this one.
See, the point is like if you have the empty set, there are no conditions on alpha, right? It's an arbitrary thing. No condition of saying it must be an isomorphism on that subset. Well, the space of all vector bundles map is contractible. Well, that's why any two such things are connected by a homotopy. I gave away the solution of the homework problem. Shoot. All right, so let me stop here. And so what we'll do in the second hour, I will show you that, I mean, this thing should already remind you of the principal symbol, right? Principal symbol was a vector bundle map, and it was an isomorphism away from the zero section. So yeah, so you can see that the principal symbol will be representing a K-theory element of something rather, and I'm going to specify that. And then it turns out, oh, the index will only depend on this K-theory class that is represented by the principal symbol. And then you're sort of in business at the topologies. You go like, oh, okay, well, then we just need to construct a map from that K-theory group to Z, which should calculate the index of this thing, right? So that's the idea. So we'll then write down what is that topological index map, and then the index theorem says, oh, the index of the operator is actually the same as what you get by the topological index map.
Should we worry that zero section is not an open set?
Then what?
Should we worry that the zero section is not an open set?
No.
Okay.
This is not final. I will next talk about K-theory with compact support. It's that in that context that will sort of, that the principal symbol will be a K-theory element. All right, thank you. All right, so second part of this talk, I want to go on and we want to interpret the principal symbol of an elliptical operator as a K-theory element. So I sort of recalled what the K-theory of a compact space X is and the relative K-theory. Now I want to talk about K-theory with compact support. This stands for K-theory with compact support. So we define that in a very similar flavor as that one here. We want to basically say, oh, we have triples consisting of two vector bundles, E plus and E minus, over that space X, and a vector bundle map between them. But instead of specifying where that thing is an isomorphism, we want to say, hey, it should be an isomorphism outside of some compact set. Alpha is an isomorphism outside some compact set. Subset of X. And then you sort of do similar equivalence relations as up there. So you're saying, well, you know, yeah, there's obvious notion of isomorphism of these things, an obvious notion of sort of adding identity map of another vector bundle, and an obvious notion of homotopies of these alphas, of course, keeping the restriction that while you're deforming, you still should have an isomorphism outside a compact set at all times. But it doesn't need to be the same set as you deform your vector bundle map. Okay, so
Is that modifying that equivalence relation? Is that the same thing as taking the co-limit of the k of x comma x mod c?
yes, I believe that this compact supported K-theory is equivalent, can equivalent be defined by taking a co-limit over compact subsets of X. Okay, so this is a very convenient way to think of this K group, right? Since now, if we have D, an elliptic operator, then we have our principal symbol, right? The principal symbol of this operator D is a map from the pullback of the domain vector bundle in the pullback of the range vector bundle. So this is the principal symbol. Of D. Then you see this is invertible outside the zero section. Of the cotangent bundle of X. So, does that have compact support? Well, if X is compact, then it has compact support. So this one here, in other words, is an element in compact supported K-theory of the total space of the cotangent bundle if X is compact. It will be convenient to think slightly more general. Well, what happens as X is not compact? It's still true that this vector bundle map will be an isomorphism away from the zero section. But the zero section, I mean, that's homomorphic to X, so that's not compact then. But we still have something which I will call vertically compact. Since if you intersect this given thing with the pre-image of a compact subset of X, then you will have, again, something which has compact support. So I will call this vertically compact. In general. So this is vertically compact. So this is compact in vertical, i.e. the fiber directions. Okay. All right, so we have for compact manifolds in particular, we have a nice interpretation of this symbol as an element in the K-theory of the cotangent bundle with compact support. And here's a cool fact, namely the index of this elliptic operator will only depend on that K-theory class. Index of D depends only on the class of that the principal symbol of D represents in the K-theory with compact support of the cotangent bundle. And this is, of course, a statement for X compact, since otherwise the index doesn't make sense. So for compact X. Depends only on that. So that brings us a step closer to saying, oh, then there should be a topological description of it, right? So then the obvious question is there a topologically defined map, homomorphism, which will be called the topological index from that K-theory group with compact support of the cotangent bundle of X into Z. And then the hope would be, well, if there's a canonical thing that we can construct using topological means, then we should hopefully prove at the end of the day that it agrees with the index. So that's sort of the goal. So that's the next thing we want to talk about.
There's some way to think about this K-theory class as being fetched from something attached to the pages on X.
Well, the symbol, the principal symbol is defined patchwise if you want to.
Yeah,
And
on the language of sort of K-theory class itself, you assemble it on the length and on the K language.
sort of like, I mean, vector bundles can be described by sort of their transition functions in the same way K-theory classes can be defined in terms of transition functions. So if you prefer that, you could use an atlas and then produce sort of transition functions for any double overlaps.
Is there any? Maybe I'm anticipating something you're going to say. Maybe this is a bad question, but I'll say it anyway.
Anticipating questions are good.
I mean, couldn't I also think about this symbol as being a class in the relative cohomology group, T star, or the K cohomology T star X, comma T star X minus the zero section?
Absolutely. Yep.
Okay.
Yep. Maybe I should write this down. So equivalently, this can be thought of as the K theory of that, comma, zero section.
I'm inclined to think about this as, wait, no, not that. T star X minus the zero
Sorry,
section.
sorry. Yeah, absolutely.
My motivation for saying this is where I always think complex design.
Okay, sounds good. Yeah, and I think in terms of compact support, so whatever is more convenient. But yeah, it's good to have both points of view down. Yes, minus the zero section. Since on this region, your principal symbol is invertible, so yeah, therefore you can view it as a relative K-theory class living in that relative everything away from the zero section. Okay, so the third part of my talk is about the construction of this top index map. So this will be a homomorphism, as I wrote down there, from K-theory. And let me write down compact support again.
So is there an equality?
And to
Previous
see.
discussion.
Is there what?
I see like a vertical equal sign that I'm confused about.
There's a vertical equal sign, yes. So this is an alternative way to think about the K-theory with compact.
Maybe the vertical?
Oh, vertically compact support, yes. Well, I guess here I'm sort of thinking about compact X anyway, and if X is compact, then it doesn't make a difference, right? But, so X is compact. But the general statement is true that this way of thinking corresponds to the vertically compact thing. So maybe I should write this down more generally. For any X, compact or not, we can identify the vertically compact version of the cotangent bundle with the K-theory of the total space relative the complement of the zero section. Yep, pretty good. Okay. But for non-compact X, we of course don't expect to have this map to Z. Right? So how do we construct this? Well, the main tool will be a topologist tool, which is a so-called Thom isomorphism. So assume that say V is a vector bundle, a real vector bundle, of, say, dimension k. Then I want to look at, I would like to sort of phrase this in a very general discussion. So let's think about a general cohomology theory, which can be K-theory, can be ordinary cohomology, or one other more general cohomology theory. So let's see, E, it's a generalized cohomology theory. So the main thing I'll be thinking of that could be K-theory, ordinary cohomology. And the thing I want about this, it should be multiplicative in the sense that it should have cup products. So with cup products. So in other words, I can take an L-dimensional cohomology class and a K-dimensional cohomology class. I can take the cup product to get a K plus L-dimensional cohomology class. Okay, then let me look at what the cohomology class of a fiber here of this bundle is. So I pick a point x, and I write Vx for the fiber of this bundle at the point x. And let's look at the cohomology applied to Vx, but I want to take with compact support. And then there are various ways to think about it. One way is to say, oh, that's the same thing as what you said. So you take the vector space Vx relative to Vx without 0. Or another way to think about it, the compactly supported cohomology is the same thing as the cohomology with, of the one-point compactification. So let me write V plus for the 1-point Vx plus for the 1-point compactification. And, well, the 1-point compactification of a k-dimensional vector space will be a k-sphere, right? So you're really talking about, oh, and reduced, yes. And that, of course, is just a sphere, so this is isomorphic to the reduced cohomology of a k-sphere. But then I can have, again, suspension isomorphism. That will say this one here is really isomorphic to the K-theory, K dimensions lower, to the unreduced E-theory of a point, K dimensions lower. Okay? So I have this sort of chain of morphisms. This is a chain isomorphisms of what kind of things are these? Well, all of these things, I can use my cup product to say they are all modules over the cohomology, the E cohomology of a point. Right? So these are all isomorphisms of modules over the E cohomology of a point. Right? Can multiply with that. So what is it saying? Well, this thing here, well, that's obviously free as a module over the E cohomology of a point. It's a free module. So that is saying that, oh, this one here is a free mod is also a free module. What's that? Oh, yeah, this is a reduced theory. So the this is defined to be the kernel of the map from E tilde of E of whatever space we're looking at under the restriction map to just E of a point. And that works for any space X. So maybe I have a general point space X here, then the reduced E theory of X is always defined as a kernel of that. So the upshot of this is that this thing here is a free module over the ecohomology of a point. All right. So that will motivate now the notion of an E orientation for a vector bundle, this vector bundle V here. Definition. An E orientation, also known as Tom class, for this vector bundle V over X, is an element tau in the ecohomology of vertically with compact vertical support of this total space, which is the same thing as what Mark likes, namely the ecohomology of space V relative to V minus the zero section. Such that if I restrict this element to the fiber over any point X, this one here is then an element in the ecohomology of this compact support of the fiber. And this should be a generator of this free module. Okay. So, for example, for ordinary cohomology, picking a cohomology class with compact support in the total space with a property that each restriction to a fiber is a generator is the same information as an orientation on this vector bundle. That's sort of where this name comes from. That's the historical origin, but you can do it with a very general cohomology theory, and we'll be in particular interested in K theory. Okay. So what is the use of this sort of E orientation? That's an important theorem. So suppose tau is, let's say it lives in E n.
So we concluded that we had a free module, but we didn't conclude that it was dimension 1. Is this
Oh, no, a free module of dimension 1. Sorry, I meant to write this of rank 1. Yes. Yeah. And that's why I want just one generator. Yes. Thank you. Now, suppose that we have an element in this thing with vertically compact support of V, that this one is an orientation, then I have a map from the E-cohomology with compact support of the base space X into the cohomology with vertically compact support of the total space of V, which works by multiplying by the Thom class. So if I have any class alpha here, then I take tau and I multiply it by alpha. So this is the cup product. In the case of K-theory, which we were interested in, this will be given by a tensor product of the bundles and vector bundle maps involved. It's a tensor product. If the cohomology theory is the K-theory. And it's the ordinary cup product if the cohomology theory is the ordinary cohomology. And is given by, if you think in terms of de Rham cohomology, it would be the wedge product of these forms. Okay, so wedge product. Wedge product if the cohomology question is the de Rham cohomology. Oh, yeah, right. So I need to, exactly, thank you. So the alpha is a class in X, and then I have the projection map from the total space of my bundle pi into the base space, and then I pull back alpha. Now notice the following thing. So we need to check that this one here, sorry, and I meant to write compact support, not vertically compact support. I meant to write compact support here. So why should this have compact support? Well, if you think about the total space here, this way, these are the sort of fibers. Here's my projection map down to X. So the class alpha has maybe support in this set here. This is the support of alpha. So then what is the support of the pullback of alpha? Well, it will be anything, colored chalk? No, colored chalk. So then the pre-image here, this is where the support of pi star alpha lives. Oh, thanks very much. And then you see, oh, if you now tensor it with this is the support of pi star alpha. Now, what is the support of this tau? Well, it has vertically compact support. So it's supported almost very close to sort of the zero section. Only on the zero section it goes sort of wrong, right? And so, yeah, this has not compact support, but if you intersect it, if you take the product with pi star alpha, then the support intersects, and so the support will be just the part of the green thing which is inside the red region. That's why you end up with compact support here. Okay, and the statement is, this Thom isomorphism theorem says that this map here is an isomorphism. Now we want to put that to good use.
It's also true if you don't have the, if you put VC on one side and no C on the other side.
That's right. That's right. Yes, you can play with these compactness conditions.
Extremely minor thing to say, star plus k, because the time
Oh,
class
yes.
is degree by k.
Yes. Yes, absolutely. No, I definitely wanted that in there. Thank you.
So in the definition of an e-top class, do you require that tau to be in degree k?
Yes. Yes.
It's there though, right? Suppose tau.
Yeah, let me just write k here.
But Tom class is equivalent in many different dimensions. You know, like in K theory, typically the Tom class lives in K equals 0. Whereas if you're dealing with regular cohomology, the Tom class typically lives in the degree of the real degree of the vector.
Right, right. Does that? Okay. Okay. Now I want to use that to construct a map in the following situation. Now suppose that x into y is a proper embedding of manifolds. Say with normal bundle n. N is a normal bundle over X. So then you can, let's call this embedding F. Then you could sort of pull the following thing. You can say, okay, well, let's start with an element. Let's start with a group, the e-cohomology with compact supports of manifold X. Let me sort of maybe assign dimensions here. So let's say this N is a k-dimensional bundle. Okay. So in other words, it's an embedding of codimension k. So then I can do the following thing. I can take an element in the e-cohomology of X with compact support, and then I can use my Tom isomorphism. Multiply by my Tom class to say, oh, that's isomorphic to the cohomology with compact support plus k of the total space of my normal bundle, right? Now, I claim there's a map of this into here, since, well, you can identify, let me just do it like this. So you have the original embedding of X into Y. Now, the tubular neighborhood of X inside Y can be identified with the total space of the normal bundle, right? That's the tubular neighborhood theorem. And so that is saying that X sitting inside N as its zero section, that can be extended to an embedding of this bigger thing. So this one here, the image is a tubular neighborhood of X inside Y. Neighborhood of X in Y, or f of X in Y. Should I draw a picture of that, or is that pretty clear for everybody? Okay. Well, so I can think of N as being sitting as a codimension 0 submanifold of Y. And this is, again, going to be a proper embedding here. It's also proper.
Should the arrow be homologies goes that way because it's complex support.
Exactly. So that's exactly the point. So I have a cohomology class in here, which is supported on some compact set thing in here. Well, under this proper embedding, that goes to some compact thing in there. And then I can say, oh, OK, just sort of then look at this class that you have here, which is supported on that compact subset. Look at it as a class here supported in that same compact subset. So you could sort of think of this map here as extend by 0, right? Say, think of differential forms. If you have differential forms that sort of are supported in a compact set, that means they're just identically 0 outside, and then you just extend by 0 outside that. So you have a map going that way. Oh, OK. So you have a map now. Let me denote this map, and let's call it F Schweik. And so notice that it sort of, it's a funny map, right? It goes sort of the wrong direction for cohomology. It goes in the same direction as the original map F. That's why I put the Schweik as a subscript to indicate that. And it makes a funny shift of degrees given by the codimension. OK, it was it is. And that, of course, uses the fact, so F Schweik can be constructed. So what did we use for this one here? The crucial thing was that we had the Thom isomorphism, right? So can be constructed provided the normal bundle N comes equipped with an E orientation. That's a crucial ingredient here, right? So this map is given by a cup product with that orientation class. And if we have the orientation class, yes, we can form this composition here. It's a crucial ingredient. So now I want to apply that. And in the application, my manifolds will be the following. So now I have smooth manifolds, embedding here, smooth manifolds, proper smooth embedding. Embedding of, say, codimension K again. It's normal bundle N. Bundle N. I don't want to apply it to this one, though. I want to rather go to the tangent space. And the differential of the original map induces a map in here, which again is going to be a smooth, proper embedding. With normal bundle, so what's a normal bundle here? Well, then you have sort of the normal bundle sort of in the base direction, right? That was N itself. But on each fiber, you see also the normal bundle in the fiber direction. So you have basically the sum of two copies of the normal bundle as the normal bundle of this sort of new embedding here. So the normal bundle is N plus N. But of course, N plus N would be a bundle over X, and I need to pull it back to the total space of the tangent bundle, pi star, where the pi is the projection map from the total space of my tangent bundle of X to X. So I get this normal bundle here. Now notice that this normal bundle here, I can think of as a complexification of N, right? sum of two vector space, you can always identify with the complexification of that vector space. So in particular, that means the normal bundle of this embedding now is a complex vector bundle. So this whole thing now becomes a complex vector bundle. Why is that helpful? Well, the helpful fact is that there is a K-theory orientation for complex vector bundles. It's often called the Atiyah orientation of complex vector bundles. But complex vector bundles have K orientation. In other words, the complex structure on that vector bundle gives you a built-in K orientation. And not today, but maybe at some future point, I will talk about the construction, how to write down this K orientation of complex vector bundles. Okay, so that means, hey, we can make this construction if our cohomology theory is K theory and the embedding we apply to is really the differential of the original embedding, right? Hence, get map. So I get a map. So we have originally the K theory with compact support of our cotangent bundle of a manifold X. And now the thing that I'm going to always do is notice that the tangent bundle and the cotangent bundle are isomorphic as bundles. Say choose a Riemannian metric, and that provides such an isomorphism. So this is via, say, a metric on the manifold X. So I'm always going to just sort of from now on work with a K theory with compact support of the tangent bundle. And then I have this map that's associated to this proper embedding, the Schwick map that will go from the K theory, compact support of X in the K theory of compact support of Y. So you might say, oh, wait a minute. Isn't there sort of the dimension shift there? Isn't there a shift here? So if I start with K0, which is a K theory as we defined it, I end up with 0 plus 2K, since that is the new codimension, right? Since the original codimension is K, then this will have codimension 2K. So I have a shift here. But then the K theory is too periodic. Complex K theory is. So no, I'm always going to identify that again with just the K theory of that. So that's why I don't have the dimension shift. Okay, so I have this map here. So now how I'm going to, this is the main ingredient in the topological index map. So now comes the definition of the topological index map. So to define topological index map, pick an embedding of your manifold X into, now we specialize our manifold Y to be just a huge sphere. Embedding. And so this should be embedding. And I'm assuming now that X is compact. So it's automatically a proper embedding. So that's my embedding F here. I also have the embedding J of a point into Sn. So then I'm going to go like this. So I want my topological index map to go from the K theory of the tangent bundle of X into the K-theory of a point, right? How is it going to work? Well, the first thing I do is I look at the induced proper embedding of the differential of f. The associated Schrieg map then brings me to the K-theory with compact support of the tangent bundle of Sn. Right? And then I have, then I apply this to the embedding of a point into Sn, right? That's also a manifold, so I apply my Schrieg map in that case. I take tangent of J and take the Schrieg of that. That gives me a map from the compact, from the K-theory of a point, from the tangent space of a point. It's all a little bit of an overkill here, but that's tangent space of a point is a point again, right? Now, this one here, this group is Z, K-theory of a point. This map here, if you think about it, hey, this is just an isomorphism. Since, yeah, think about it, and this is an isomorphism. It's just a... So that is what we want, right? We have now constructed by topological means a map from this group into this group. That's defined to be the top index, topological index map. So now the index theorem is sort of the statement, hey, those two things agree. Index theorem. And that's due to T.N. Singer. And there are many, many different ways to formulate the index theorem. It can either be formulated as a theorem for a general elliptic operator, the way we do here. It can be phrased or for concrete operators like the Dirac operator and Dolbeault operator, etc., pp. Or it can be phrased in terms of K-theory, like we did here. Or it can be phrased in terms of cohomology. So there are lots of different versions. So this is, to me, the version that is maybe most encompassing for the time being, but also probably hardest to work with, since this topological index map is a little mysterious, right? That becomes a lot more hands-on, and for calculations, you want to say that in cohomological terms rather than K-theory terms. But that's a translation. So this version of the index theorem is the K-theory version as opposed to the cohomology version. And it just says that if D is an elliptic differential operator on a compact manifold X, then the index of D is actually can be calculated in this topological way. Namely, you start off with the principal symbol of D. This represents an element in the K-theory with compact support of your tangent or cotangent bundle of X. And then you can use these maps here, namely the top index map defined over there, to get an element of the K-theory of a point, which is C. So that's the statement. So the left-hand side is sort of the analytic side, where you talk about the index of an elliptic operator, and the right-hand side, that's pure topology, and you're talking about K-theory classes, and you push them around, right? Okay. So in the last few minutes, let me sort of outline how the proof is sort of working. So this is a very, very, very rough outline. define proof. So the right-hand side has a nice formulation in terms of this topological index map, which is just a homomorphism from a K-theory group into the K-theory of a point. Now, it would be nice to also have such a formulation for the left-hand side. And there is such a thing. You define an analytic index map homomorphism, which has the same domain and range as the topological index map, namely the K-theory with compact support of the cotangent bundle of X, and the range is K-theory of a point, which of course is Z. But this map is defined in a very different way. It starts with any class sigma in here, any class U maybe. And then what you do is you say, oh, we know that the index of an elliptic operator does only depend on its principal symbol. So let's try to construct an elliptic differential operator which has U as its principal symbol, and then take its index, right? So you take the index of D, where D is any elliptic differential operator with the principal symbol of D equal to the given U in the K-theory of the cotangent bundle. And so the only question is, well, can you, for every element in this K-theory, can construct such an operator? And yeah, that sort of means to do that. So then it's really boiling down to saying, well, you have these two different, totally differently defined homomorphisms, and you want to show that they are the same. So I need to show that the analytic index map is equal to the topological index map. So to do that, you study certain properties of this analytic index map. And that's really where all the hard work is. Here two properties. The first one is really simple. The second one is the real tough one to show. So the first one is, well, what happens if you do it for a point, right? So if you look at the analytic, so if X is equal to a point, then the analytic index map is a map from the K-theory of compact support of the tangent bundle of a point, right? Well, that's still a K-theory of a point into K-theory of a point. You want to say, oh, that's the identity map, right? So that's not hard to show, since we totally understand elliptic operators on a one point. Okay. The second property is really a tough one. So let me look at the analytic index map. So that's a map from the tangent bundle of your manifold X into K-theory of a point. So that's the analytic index. And let me indicate which manifold we're on. So this is the analytic index map for the manifold X. Now, suppose that I have an embedding of X into Y. So proper embedding Yeah, this is, I mean, it's an embedding. It's always automatically proper, since I'm assuming that the manifolds we're talking about are compact, right? Only for compact manifolds does the definition of the analytic index map make sense. So then I have the analytic index map for the manifold Y as well, for this bigger manifold Y. But these things are related via this, this embedding here, right? Since we said in this construction up there, whenever we have an embedding of these compact manifolds, we get a proper embedding of the tangent spaces, and that induces this map that we called TF Schwick. So here's the map TF Schwick. This one here, the statement is that this diagram is commutative. Okay. All right, so this is the hard part. This is easy to show, and this is hard analytical work to show this. But once you have that, you're home free. So the rest is totally formal. Okay, so let me now look at the analytical index of an element U. Right. So by definition, this is analytical index from the what am I saying? So the first thing I'm going to use is I'm going to use the second property here to embed X into some huge sphere by embedding F. Right, then by the second property here, I have this commutative diagram here. So this is the same thing as the analytic index for the sphere of the class that I get by transporting the class over via this map here, right? Now, let me again use this embedding of a point into Sn, call this J. And then I have the corresponding Tj perp. That's a map from K-theory of a point into K-theory with compact support of the tangent space of the large N sphere. And the point here was that is an isomorphism. So I can rewrite this one here in a totally artificial way as T of, I apply Tj Schwick inverse to this element, and then I apply Tj Schwick again. Right? That way, that's the identity, so that doesn't do anything. So this is obviously the same as this one here, right? Everybody happy so far? Okay, now I use part 2 again. So by property 2, but now applied to J. This is saying, oh, the analytical index of Sn applied to this Tj, that's the same thing as the analytical index of a point applied to that stuff here. Tj Schwick inverse times Tf. Right? Just formal. But the analytic index for a point, oh, this is supposed to be the identity by part 1, right? By property 1. So this doesn't do anything. So this is just that. This is just Tj Schriek inverse times Tf Schriek applied to U, right? But that was our definition of the topological index applied to U. So that's by definition. Okay, so that proves the Atiyah-Singer index theorem, if you know this hard property there. Let me just sort of make a comment here. The next sort of topics that would be natural to explore would be to say, oh, it's kind of interesting. So as far as index theory goes, it's really about the K-theory of that with compact support of the total space there. So now you could ask, oh, so don't we have the Thom isomorphism for this thing here? So that this is really isomorphic to the K-theory of X, right? The answer is, well, yeah, but you need the orientability, right? So the question is, for which X is the tangent bundle K-orientable? And it turns out that, well, if X is a spin manifold, that gives you an K-theory orientation. Actually, you need slightly less. You just need a spin C structure, but it's easier to think of spin structures for me. So a spin structure will do the job. Oh, and then you have an interesting question. So, okay, assume that X is a spin manifold then, so that you have this Thom class, this K-theory orientation. Then you could ask, well, so then you have this sort of very specific, very sort of primordial class there, namely the K orientation of that, right? What operator does it correspond to? Like this E orientation is sort of the mother of all K-theory classes in the sense you get any other K-theory class of the total space with compact support by just multiplying by an element in the K-theory of the base space. So in that sense, the K orientation is sort of the mother of all K-theory classes of that total space. So then you could ask, okay, what is the mother of all operators, right? Meaning an operator, what is the operator whose principal symbol is exactly that Thom class? And the answer is, that's the Dirac operator. Okay, well, how do you get all the other symbols? Well, you get all the other elements in the K-theory of Tx by taking your Thom class and multiplying with something that you pull back from your manifold. Okay, the principal symbol of what operator is that? Well, it's the principal symbol of the Dirac operator twisted by a vector bundle on your manifold X. So in that sense, if you have a spin manifold, it's very natural to think of these differential operators just to dispense of most of the differential operators and just talk about Dirac operators twisted by vector bundles. These are all very special from an analytic point of view since they're all first-order elliptic differential operators. But for index theory purposes, I mean, they generate the whole K-theory of that. So from index theory purposes, there's no reason to look at all these sort of other elliptic operators. And so a natural extension would be to say, okay, well, let's construct the Dirac operator and the twisted Dirac operator. And then the other part is, well, okay, how do you calculate the index of twisted Dirac operators in more explicit cohomological terms? So these are the other parts that I hope to do maybe at the beginning of the fall semester. Thank you. Any questions? Go ahead.
The definition of the topological index reminds me of the Pointryagin-Montan construction. If you replace KC with Bordism, and it looks like you get the Bordism class of you get a map from the Bordism theory of a manifold into the Bordism theory of a point.
Mm-hmm. Yes. No, your reaction is exactly correct. If you write down this, what I call the extension by zero map for K-theory classes with compact support. If you write this down in terms of sort of Thom spaces, what you see is a collapse map that collapses, say, everything outside of a tubular neighborhood to a point. And you can describe these things in that term. But this collapse map is also the main ingredient in the Pontryagin-Thom construction. And so yeah, these things are intimately related.
And like, think about embedding this TGA streak. That sort of reminds me of the alternate description of Pointryagin-Thom construction in the case of frame vorticen, which is you take the inverse image of a regular value of the embedding of the map from your manifold into Sn. It's like if you're doing a manifold to framing, then that gives you a map. That gives you a map. Sorry. Oh.
That's okay. All right, any other questions?
So, sorry.
Go ahead.
If we think about our very basic analytic example, the Laplacian, so the topological part becomes trivial, right? Because the symbol is the identity, so the K theory class is 0.
Yes, yes. Or another way to see that, hey, the Laplacian is self-adjoint, right? So the dimension of the co-kernel is equal to the dimension of the kernel. So, yeah. Mm-hmm. Yeah.
Just historically, was this sort of understood in special cases, and Atiyah and Singer sort of had the insight about how to make it general through this Thomite sort of? I mean, what was the rough chronology?
There are definitely precursors to the Atiyah-Singer theorem. So, for example, there's the signature theorem by Hirzebro, which expresses the signature of a manifold, which is a topologic invariant, in terms of characteristic numbers, which are different topologic invariants. But then if you use Hodge theory, you can identify the signature with the index of a differential operator. And then you can say, oh, so he proved the index theorem for this very particular differential operator. And then there's sort of, I think historically also before this came the Dolbeault operator. So you roll up the Dolbeault complex into one operator, and you ask, well, how do you calculate that index? And that index turns out to be the Todd genus of this manifold. And I think that is another case that was done first before this most general thing was done. But I think the Todd genus probably was also done. The Todd genus was defined by Hirzebro, but I don't know that he had the theorem saying that that's equal to the index of the Dolbeault operator. And so
it wasn't defined by Todd.
And yeah, good question. The name strongly suggests it just belies my heritage, I guess, coming as a student of Hirzebro. I think, oh yeah, that was Hirzebro with his multiplicative genera, right?
There was also something called the Rochlins theorem, which could have been. I don't remember what was the chronology there.
Yeah, that was definitely before, and it is a pre-theorem which says, well, the signature of a four-manifold, which is spin, is divisible by 16, and now it can be viewed as a falling out immediately from observing that the Dirac operator has a quadratic structure in dimension 4, and hence its index must be even. And yeah, so there's a lot of precursors. But Atiyah and Singer were the first ones to construct this Dirac operator on a general spin manifold. And that was sort of the key to then sort of get everything. And all right, thank you.
Thank you.